Hello everyone, and welcome to the presentation on microgrid design and cost optimization using Modelica. The paper that I am presenting today is the result of a collaboration between Modelon and the National Research Council of Canada, or the NRC. The NRC is Canada's largest R&D organization, performing research in sustainability, digital technologies, AI, human health therapeutics, and many other areas, with research centers located across the country. Modelon has been working with our team at the NRC on multiple integrated system model applications and has supplied the modeling framework that you will see today. As part of our energy systems research, the NRC is currently constructing a microgrid testing and training facility that will be located in Vancouver, BC, on the west coast of Canada. The facility will include a variety of distributed energy resources, shown on the left, including a variable speed generator, solar photovoltaics, a battery energy storage system, and a combined heat and power generator fueled by biomass. As a complement to this physical testing facility, a virtual modeling and simulation capability is also being developed using the Microgrid Modelica library created by Modelon. The integrated system model for this new facility is shown on the right. To work with this integrated system model, a case study was devised consisting of 3 different use cases for a remote community in northern Canada, Whale Cove, Nunavut, shown circled on the right. Use case 1 represents Whale Cove's current configuration, a remote microgrid with no grid connection and 100% reliance on diesel generator power. The second use case considers the impact of adding renewables and energy storage to the existing microgrid. And the third transitions the microgrid from island mode to grid-connected mode, with a grid tie to a neighboring provincial utility. For renewables and energy storage, the technologies currently planned or included in the NRC facility power network were explored to see how they might benefit the existing Whale Cove microgrid. Multiple design, economic, and environmental analyses were then performed. In the next few slides, we will review each component model included in the microgrid application framework. The first model is the diesel generator. Although multiple generators exist at Whale Cove, for simplicity they were modeled as a single generator with a fuel consumption versus power correlation derived from the actual Whale Cove generator curve, shown on the right. The generator was constrained to operate above a minimum loading level of 96 kilowatts based on the operation of a single generator. To determine the available capacity of the microgrid for renewables, we looked at the difference between the maximum electrical load for Whale Cove of 402 kilowatts and the minimum loading level of the maximum generator capacity of 186 kilowatts, showing that there was room for 216 kilowatts of power to be provided by renewable energy sources. Next, we have the combined heat and power, or CHP, generator model. The CHP generator was assumed to have a fixed power output of 40 kilowatts of electrical power and an estimated cost of $0.78 Canadian per kilowatt hour, based on delivery, shipping, storage, tax, and labor costs. The PV output power was supplied as a variable input to the integrated system model, with data taken from NREL's PV watts calculator. Based on a fixed power output from the CHP generator and an overall microgrid capacity of 216 kilowatts for renewables, the PV system size was set at 176 kilowatts. The data for Whale Cove, based on multi-year weather data averages, is shown in the chart on the left. In addition, in the absence of load data collected directly from Whale Cove, load data from Old Crow, a representative northern community in the Yukon, was used and scaled to maintain the maximum load constraint of 402 kilowatts for Whale Cove. This data is shown in the chart on the right. The energy storage system was modeled based on a real-world battery system previously tested at the NRC Vancouver's battery testing facilities. The pack modeled had an overall capacity of 42.2 kilowatt hours with a maximum 2C charge and discharge rate and a min and max operating point of 20 and 80% state of charge respectively. The grid was modeled as an ideal grid with constant voltage and frequency. The details surrounding the grid are based on an actual case study that was performed to look at the economic feasibility of connecting multiple Nunavut communities to the Manitoba electric grid. The transformers and inverters required by the system were characterized using linear efficiency-based models. With respect to control and economic analysis, the microgrid manager includes both a microgrid control element as well as an economy model, which can compute the operating costs for each of our power sources. The first simulation that we ran was for use case 1, operating in a diesel-only configuration. This included the diesel generator, the microgrid manager, and the Whale Cove load. Looking at the chart on the right, you can see that the diesel power is shown to correctly track load over the course of the simulation, with a slightly higher power output level than the consumer load to cover the upstream losses and station loads. To produce the power needed over the course of the year, 609,000 litres of diesel was consumed at a cost of about 2.2 million Canadian dollars. In addition, about 1,644 tons of CO2 equivalent emissions were produced. To validate our simulation results, we computed the same results in Excel to confirm that all calculations were correct. Once verified, we then looked at the results from the local utility to see how these results compared to real-world values for Whale Cove for the total energy generated, consumer load, fuel consumption, emissions, and for cost. Note all of the costs in our presentations are in Canadian dollars. As you can see in the table shown, the load data and the total power generated compare fairly closely, with the most notable difference seen with respect to fuel, emissions, and cost, which of course are directly related. When we looked a little closer, we saw that the utility actually used a fuel efficiency value that was much higher than the value that we had derived from our fuel consumption curve shown previously. A later study was identified with more recent data, which showed a fuel efficiency value that was much closer to the value that we had been using, and essentially, based on this, the diesel consumption rates were deemed to be acceptable and were retained for the remainder of the analysis. The diesel-only case is an important one because this becomes a baseline for all of the other use cases that we're going to look at going forward once we start adding renewables and energy storage. So this will sort of be the benchmark that will allow us to see whether or not we're actually making any improvements by adding renewables. Now that we've shown that the results of our diesel-only simulation are reasonable with respect to real-world results, we can now move on to use case 2, where we're adding renewables and energy storage to the microgrid. For reliability, the diesel generator was not permitted to operate below 30% of its rated capacity, with the CHP system and PV output meeting the remaining demand. Batteries were directed to discharge power when a shortfall was detected and to charge power when there was a surplus, up to a maximum of a 2C charge or discharge rate. To validate our simulation results for use case 2, we looked at 2 seasonal cases, one day in the winter and one day in the summer. To start off, we did a simple power balance to make sure that the power supplied from all sources matched the consumer demand. In this chart, you can see that the CHP system is providing the continuous 40 kilowatt output, allowing the diesel generator to actually track below the overall load compared to the runs that we saw with the diesel-only configuration. As the PV power comes online, you can actually see the corresponding decrease in the diesel generator output, which is what we would expect. In this chart, we show the comparative results between use case 1 and use case 2 for fuel consumption, as well as CO2 equivalent emissions and operating costs. As you can see in the table, adding renewables and energy storage has decreased the total energy generated, the diesel fuel required, the CO2 emissions, as well as the cost. Now we move on to the second test case, looking at day 220 in summer. As you can see, there is such a significant surplus of power that the diesel generator is actually being forced to operate well below its minimum loading constraint. And this is not what we want to see. In order to resolve this, we introduced curtailment into the model. And by curtailment, in this case, what we mean is taking the CHP system offline and curtailing any excess PV power. As you can see, with curtailment, the diesel generator tracks much more closely to its minimum operating constraint. Looking at the battery chart in the bottom right, you can see how the battery responds in the presence of surplus power. When there is surplus power available, the battery charges up to its maximum state of charge, after which point excess PV must be curtailed. once the PV output begins to decrease and the net power is less than zero, the battery is able to discharge and supply all the stored power back to the microgrid. Having now seen how operational strategies differ between seasons, we decided to run a full simulation for the full year to determine which days could benefit potentially from CHP and PV curtailment. In the bottom left, you can see that between day 50 and day 300, there is enough surplus power on a continuous basis that these days may benefit from operating with curtailment. And you can see what that looks like in the chart on the right. The table below shows the results of 3 different simulations. The first shows the results of operating the system curtailed all year round. The second shows the results of seasonal curtailment, so curtailing the power only when the net power is greater than zero, or there's a surplus of power. The third is the diesel-only use case for comparison. And as you can see, the benefits of seasonal curtailment are clearly shown with respect to diesel fuel consumption, CO2 equivalent emissions, and cost. The next simulations that we ran were to consider the impact of changing PV installation size on the overall cost, fuel consumption, and emissions. All of these simulations were run with curtailment, so without the CHP system online and with any excess PV curtailed. And although cost decreased with increasing PV size, at some point the amount of additional power that could effectively be used versus power that had to be curtailed starts to decrease, so that your benefits start to decrease as you increase in PV size. The next design consideration is battery size. In all previous runs, looking at CHP operating only or PV operating only, there was always substantial surplus power that needed to be curtailed in order to maintain balance, implying that the battery was largely undersized for this installation. To evaluate further, multiple simulations were run with PV only, CHP only, and with both PV and CHP combined to determine the battery size that eliminated the need for curtailment. With the PV operating alone without CHP, we needed 20 times the original battery size. For CHP operating alone, we needed 10 times the original battery size. For both PV and CHP combined, we needed 1,100 times the original battery size. So we're getting to a very expensive battery. With seasonal operation, however, we can operate with PV and CHP with curtailment in the summer with only a 20 times the original battery size. And you'll notice that the 1,100 times versus the seasonally curtailed simulation results with respect to cost and fuel actually produce the same benefit. So this is an important result. And note that the black line, the black dashed line at the top of each of these charts represents the original diesel-only configuration. So we're seeing some significant benefits. The next step is to start looking at the investment cost for each of these renewable components that we'd be adding to the microgrid. For PV systems, the cost was $2.85 Canadian per watt AC, so including inverter costs. For the battery, we're looking at a cost of 509 Canadian dollars per kilowatt hour, which includes the battery management system as well as the inverter costs. And we're looking at approximately 290K for the 40 kilowatt CHP generator, which works out to be about 725 Canadian per watt AC. Looking at the table on the right, you can see that by far the seasonal operations with the 20 times battery is the best operational scenario for this particular facility, with a break-even point at about 3 years, and certainly very significant reductions in emissions, operating costs, and a very high annual savings. Moving on to use case 3, we now introduce grid-connected operation of the microgrid. We'll maintain the original battery size for this study, as the grid connection will now provide an alternate load for the case of surplus power, as well as an alternate source for the case of a shortfall. In both cases, the grid will only engage once available battery capacity has been used. Looking at the chart on the right, you can see an immediate difference in how the system operates with the addition of the electric grid. One of the most important things to notice is that the diesel generator is now operating continuously at its minimum loading value of 96 kilowatts. CHP continues to operate at 40 kilowatts, and any remaining demand is satisfied through the grid, through power supplied by the grid. In the previous slide, we were looking at day 0, which was the winter case. On this slide, we are now looking at day 220, which is the summer case, without CHP curtailment. And as you can see, with the excess power, because of the higher levels of PV output as well as lower demand, we actually see a significant amount of power having to be sold back to the grid. When we rerun the simulation with curtailment, we can actually see that the amount of surplus power has decreased significantly. And this is important because the amount of money that you get for selling back to the grid is significantly less than the cost of generating the power in the first place. So by curtailing CHP, we can actually save operational costs. The table on the left compares the results for the 3 different use cases considered, with use case 3 showing by far the greatest benefits with the addition of the grid. We can see a similar trend for day 220 with even greater improvements shown with CHP curtailment in use case 3B versus the case of no CHP curtailment in case 3A. Looking at the economics, as expected, use case 3 with seasonal operation greatly improves operational savings compared to use case 1 with diesel-only operation and use case 2 with seasonal operations. However, with full CHP curtailment, even more savings can be realized, as in this case, the cost of producing CHP power is greater than the cost of purchasing power from the grid. However, due to higher initial investment, it will take much longer to recoup costs. In addition to the rule-based simulation, optimization tools are also available for the Modelon Microgrid library using the Optimica compiler toolkit. A cost optimization was performed for use case 3 with the objective function seeking to minimize the total cost while assigning a penalty to rapid changes in battery power, diesel power, or CHP power. In addition, the diesel generator was constrained to operating at or above its min-loading level of 96 kilowatts. Looking at the chart on the right, we can see that the optimization immediately converged to the solution that involved full curtailment of the CHP system. So the CHP is operating at 0 kilowatts, the diesel generator is operating at its min-loading level, and the grid is making up the remaining power required. Where in the last slide we were looking at day 0 in the winter, on this slide we are looking at day 220, a day in the summer. Although the results are very similar to what was seen previously in the rule-based simulation, there is one notable difference with respect to the battery operation. As you can see in the chart on the bottom right, the battery is very gradually being charged and discharged over the course of the simulation. In the rule-based simulation, looking at the chart at the top, we can see that there is a much higher charge and discharge rate for the battery at the 2 points in the system where there's either a surplus or a shortfall. When compared with the optimization results, this is less optimal for the health of the battery and for the long-term life of the battery.